Imagine this traveller you did not arrive here by accident. Something in the quiet machinery of the universe placed this moment in your path the moment we speak of a comet, doing what no comet has ever done. What are the odds that an interstellar traveller would begin pouring 40 kilograms of water every second into the cold, airless dark as if breathing, where no breath should exist? Picture it a silent shape gliding past the orbit of Mars, leaving a faint green whisper of nickel and cyanide behind it, a message perhaps hidden in radiation and light. Stay with me, let's drift a little deeper. In October 2025, Blue Origin conducted another suborbital mission, using its New Shepard launch system. The capsule lifted off across the Kármán line experienced microgravity for a brief period, then returned safely under parachutes to its designated landing zone in the Texas desert. By all operational metrics, it was a success. It was the company's 15th crewed mission, and the flight profile closely resembled previous ones. Under normal circumstances, such an event would generate significant public interest, live streams, commentary, trending posts across social networks, and extensive media coverage. However, this mission was received with an unusual absence of attention. Major outlets referenced it only briefly. A handful of journalists mentioned it in passing. Social media, which typically amplifies even minor aerospace events, was nearly silent. Even more striking was the lack of the familiar visual material typically released after Blue Origin flights, interior cabin footage reactions from the crew, and promotional imagery designed to reinforce the narrative of accessible commercial spaceflight. These images did not appear. Their absence created a noticeable contrast with the company's prior communication patterns. This silence raises legitimate analytical questions. Why did spaceflight, an event that inherently symbolizes technological progress and scientific achievement, fail to generate the public engagement typically associated with such endeavors? Part of the explanation may lie in the normalization of commercial space launches. As more missions occur, novelty declines, and the public becomes desensitized to events that once felt extraordinary. However, this explanation alone does not account for the sharp disparity between this mission and the previous one conducted only 6 months earlier. The April 2025 New Shepard mission received a disproportionate amount of attention, partly due to the presence of high-profile passengers. Celebrity involvement amplified the visibility of the launch, but it also triggered large-scale scrutiny. Social media users analysed video frames, questioned physical details of microgravity behaviour, and debated perceived inconsistencies in hatch mechanisms and capsule appearance. The high visibility of the participants created fertile ground for conspiracy theories, and this resulted in a feedback loop of increasing attention. In contrast, the October mission featured a mystery passenger later revealed to be a private individual who requested anonymity before the flight but consented to being named afterward. Anonymity in itself is not uncommon, as private clients may request discretion. However, in this case it became another component contributing to the wider sense of narrative emptiness. Instead of curiosity about the identity, the public reaction was muted. The lack of questions, discussion, or speculation stands in stark contrast with the typical behaviour of online audiences. This discrepancy highlights a broader pattern. Public engagement with aerospace events is not purely driven by technological significance or scientific importance. Instead, it is often shaped by socio-cultural variables, celebrity involvement, controversy, novelty, and emotional resonance. When those elements are absent, engagement declines sharply, even when the underlying event remains scientifically relevant. However, the silence surrounding this mission also produced a secondary phenomenon, reflective speculation. When a normally visible process occurs quietly, observers who pay close attention to aerospace developments naturally question the deviation from the expected information pattern. The lack of imagery, commentaries, and supplemental data triggered a line of inquiry that asked not whether anything physically anomalous occurred during the flight, but whether something socially anomalous occurred afterward. This shifts the focus from engineering analysis to the sociology of information. Why was the communication pattern different? Was it a deliberate decision by the company? Was it an artifact of media cycles overwhelmed by other news? Or was it the result of no longer having celebrity amplification? This is where cognitive bias becomes relevant. humans are predisposed to find patterns in noise and significance in silence, especially when silence deviates from expectation. A void of information is often interpreted as intentional even when it may be accidental or benign. In this case, the absence of typical post-flight material created an interpretative void that some observers filled with questions that, while speculative, were logically rooted in deviation from past precedent. Comparing the April and October missions reveals a symmetry. One mission produced a saturation of visibility, the other produced an almost total absence. This contrast can lead to further inference making, even if both events were operationally straightforward. In the April mission, overexposure bred skepticism. In the October mission, the underexposure bred suspicion. Both reactions illustrate the modern dynamic between spaceflight public perception and the rapid interpretation of information gaps. Ultimately, the scientific perspective requires restraint. The silence surrounding the October flight is noteworthy, but not necessarily evidence of irregularity. Communication strategies vary. Media attention fluctuates according to unrelated cultural forces. The absence of images or extensive commentary may reflect operational decisions or shifts in marketing priorities rather than concealment. However, from an analytical standpoint, the event is valuable because it demonstrates a fundamental principle. In the modern information landscape, anomalies are not always physical. Sometimes they are informational. A missing video, a missing headline, or a missing social reaction can appear as significant as an engineering anomaly to those accustomed to tracking patterns in aerospace reporting. Understanding this helps distinguish between scientific irregularities and irregularities in public discourse. Thus, this silent flight serves not as evidence of hidden events, but as a case study in how the absence of expected signals can shape interpretation. It illustrates the intersection between spaceflight psychology and communication patterns in the contemporary digital environment. In a scientifically grounded view, the flight happened exactly as documented, but the reaction to its silence presents a meaningful opportunity to study how humans interpret anomalies, not only in the sky, but in the narratives surrounding our attempts to reach it. Modern astronomy is entering a period defined not only by technological progress, but also by an increasingly complex relationship between data interpretation and human cognition. As telescopes, detectors, and computational tools expand the boundaries of observation, astronomers are confronted with growing numbers of anomalies, signals, objects, and light curves that do not immediately fit established models. These anomalies are scientifically valuable. They force researchers to re-examine assumptions, update theories, and refine their understanding of cosmic processes. Yet they also reveal something equally signiicant: the psychological frameworks through which humans make sense of the unknown. Human beings are pattern-seeking organisms. This evolutionary trait, once essential for survival, now shapes the way we interpret scientific ambiguity. When confronted with a phenomenon that lacks a clear explanation, the mind instinctively constructs narratives to fill the gaps. This dynamic is clearly illustrated in the global reactions to astronomical enigmas such as Oumuamua and Tabby's star. Both objects presented researchers with datasets that resisted immediate classification, and both triggered widespread speculation that extended far beyond conventional scientific discourse. Oumuamua, detected in 2017 as the first known interstellar object to pass through our solar system, displayed unusual characteristics. A highly elongated shape, rapid tumbling, no visible signs of outgassing, and a slight non-gravitational acceleration that could not be easily attributed to conventional cometary activity. Scientists propose several plausible physical explanations, such as sublimation of unseen volatiles or solar radiation pressure on a low-density structure. However, the lack of direct observational evidence left room for uncertainty, and into that uncertainty entered the idea of an artificial origin, a probe, or light sail created by an extraterrestrial civilization. While this hypothesis remains unsupported by empirical evidence, it demonstrates how ambiguity invites higher impact interpretations, even when lower impact explanations remain statistically more probable. A similar pattern occurred with Tabby's star, whose irregular and non-periodic dimming events prompted early conjectures about megastructures or alien engineering. Subsequent observations indicated that dust clouds were a far more likely explanation, yet the initial fascination with more spectacular scenarios illustrates the human tendency to attribute intention or agency to unexplained patterns. This inclination emerges not from irrationality, but from deep-seated cognitive mechanisms. Humans evolved to detect meaningful signals in noisy environments, and this predisposition persists, even when the predators and patterns have become abstract and cosmological. Psychologists identify several cognitive biases that shape these interpretive tendencies. Pattern recognition leads observers to perceive structure even in incomplete datasets. Hyperactive agency detection encourages the attribution of intentionality to ambiguous signals, a bias that once helped early humans detect threats, but now influences interpretations of astrophysical anomalies. Confirmation bias causes individuals to favour explanations that align with pre-existing beliefs or expectations. Meanwhile, the emotional appeal of extraordinary explanations ensures that high-impact hypotheses such as extraterrestrial intelligence receive disproportionate attention regardless of their probability. These biases do not negate the scientific value of anomalies. In fact, many major astronomical discoveries originated from initially inexplicable observations. Pulsars were first catalogued as LGM-1 little green men because their precise periodicity seemed unnatural. Gamma-ray bursts were detected without clear origin, and were for years a source of scientific confusion before being linked to supernovae and neutron star collisions. Each case demonstrates how anomalies can serve as catalysts for scientific advancement, even when early interpretations include speculative or incorrect hypotheses. However, the challenge of modern astronomy lies in balancing this imaginative impulse with methodological rigour. The sheer volume of data now generated by contemporary surveys and observatories means that anomalies are far more frequent than in previous decades. Automated sky surveys produce terabytes of data each night, revealing countless objects that behave in unexpected ways, simply because the observational field has grown so vast. Not every anomaly indicates new physics. Many reflect incomplete data, instrumental noise, or rare but natural events that existing theories do not yet model well. The interaction between public perception and scientific interpretation further complicates the landscape. In an era of instantaneous communication, anomalies can reach global audiences before scientists have time to analyse them. This dynamic shapes the narrative around astronomical discovery long before scientific consensus forms. Speculative theories spread faster than peer-reviewed explanations, and the emotional weight of high-impact ideas often overshadows more moderate interpretations. This does not mean the public is misguided. Rather, it reflects the human desire for meaning in a universe that often presents more questions than answers. Understanding these psychological dynamics is essential for interpreting not only the anomalies themselves, but also the discourse surrounding them. Scientific uncertainty does not inherently justify fantastical explanations, and skepticism does not require dismissing anomalies outright. The key is to maintain a balance between curiosity and discipline, between the willingness to imagine possibilities and the commitment to evaluate them rigorously. Astronomical anomalies therefore serve a dual purpose. Scientifically, they challenge existing models and push theorists to develop more accurate descriptions of cosmic behaviour. Psychologically, they reveal the ways in which the human mind navigates ambiguity, projecting its structure and biases onto phenomena occurring at interstellar distances. In this sense, every anomaly is a mirror. It reflects not only the complexities of the universe, but also the complexities of human cognition. The path forward requires acknowledging both aspects. As technology continues to expand our observational reach, the number of anomalies will only grow. Some will resolve into well-understood natural processes, others may remain unexplained for years, and a few may genuinely point to new physics or new astrophysical categories. Progress depends on approaching each anomaly with a balance of imagination and restraint, and awareness that the cosmos is vast enough to surprise us, yet consistent enough to demand evidence. In the end, astronomical anomalies illuminate two frontiers: the external frontier of the universe itself, and the internal frontier of the human mind attempting to understand it. Recognizing this duality allows us to engage with cosmic mysteries in a way that is scientifically grounded, intellectually honest, and cognitively aware. Interstellar objects represent one of the most profound scientific opportunities of the modern era. Unlike the familiar comets and asteroids that orbit within the gravitational well of our own solar system, these bodies originate from entirely different stellar environments. Each carries frozen within its composition a chemical and mineral record of a star system we will never visit. In this sense, interstellar objects serve as inadvertent messengers, natural archives preserving the conditions of worlds that formed under different radiative fields, metallicities, and thermodynamic histories. When such an object enters our observational reach, it provides a rare direct sample of planetary chemistry from beyond the Sun's dominion. The diversity observed among the 3 confirmed interstellar visitors Oumuamua, 2e Borisov, and 3 Atlas illustrates this concept clearly. Although the sample size is small, the compositional differences are already striking enough to suggest that our solar system's materials are far from universal. Oumuamua, for example, exhibited no detectable outgassing, despite its unusual acceleration leading to hypotheses involving exotic volatile ices or radiation pressure-driven dynamics. Its shape-rotational state and lack of typical cometary signatures distinguished it sharply from solar system analogues. In contrast, Tsuaya Borisov resembled a conventional comet in behaviour but not in chemistry. Its carbon monoxide abundance exceeded that of most local comets, implying formation in a particularly cold and volatile rich disk. Now, 3I Atlas introduces further deviations: high CO2 dominance, delayed cyanide activation, unusual water production rates at great distances, and the puzzling presence of nickel unaccompanied by iron. These 3 samples, each chemically distinct, collectively demonstrate that the diversity of planetary formation environments across the galaxy is vast. While solar system comets share a relatively narrow range of compositions due to their shared origin in a single protoplanetary disk, interstellar comets represent a much broader distribution. They carry signatures of star systems with different temperatures, radiation environments, pressure gradients, and histories of elemental enrichment. In this respect, every interstellar object is not simply an asteroid or comet. It is a geological and chemical data point embedded in the larger mosaic of galactic evolution. The possibility that certain comets might contain unusual molecular species not merely rare within our system, but entirely absent is scientifically plausible. Chemistry in protoplanetary disks is governed by local conditions such as temperature density, radiation flux, and the availability of precursor molecules. Variations in these parameters can lead to different pathways in ice formation, organic synthesis, and mineral crystallization. It is conceivable that planets forming around young stars, especially those formed early in the galaxy's history, produced cometary bodies with compositions that have no analogue in our environment. As more interstellar objects are detected and analysed, the periodic table of astrophysical chemistry may expand to include unexpected volatile ratios, unusual organic structures, or exotic ices stabilised under conditions unfamiliar to Earth-based laboratories. This potential diversity raises deeper implications regarding the distribution of life's building blocks across the galaxy. Panspermia hypotheses, although unproven, are rooted in the idea that organic molecules or prebiotic chemistry can be transferred between star systems by natural carriers. While the survival of complex biomolecules during interstellar transit is constrained by radiation and timescales, simpler organics can persist if buried within sufficiently thick layers of ice and dust. The detection of organic compounds, cyanide and carbon-rich volatiles in interstellar objects suggests that such chemical inventories may be widespread. If so, the seeds of prebiotic chemistry could be more ubiquitous than previously assumed. At the same time, the speculative idea that interstellar objects might carry technological signatures cannot be dismissed outright, even though there is no supporting evidence in the case of any known object. From a purely theoretical perspective, an advanced civilization could exploit natural comet-like bodies as protective shells for long-duration probes or archival data. Such objects could traverse interstellar distance for millions of years shielded from radiation and micrometeoroids. An artificial signature embedded within apparently natural materials might be detectable only through anomalous elemental ratios or unexpected isotopic distributions. Although purely hypothetical, such considerations highlight the need for open-minded yet disciplined approaches to anomaly interpretation. The scientific community's path forward involves constructing a comprehensive catalogue of interstellar object compositions, trajectories, and physical properties. With upcoming surveys such as the Vera-Rubin Observatory detection rates are expected to increase dramatically, potentially transforming the field from one defined by rare discoveries to one supported by statistically meaningful samples. As the catalogue grows, patterns may emerge. Certain stellar populations may produce comets with characteristic volatile ratios. Regions of the galaxy influenced by particular types of supernovae may yield objects enriched in specific heavy elements. Variations in metallicity among birth clouds may correlate with organic abundance or structural mineralogy. Over time, interstellar objects could become critical traces of the galaxy's chemical evolution. Among the many signatures these objects carry, metal ratios, particularly anomalies, such as 3C Atlas's nickel without iron, may be especially informative. Nickel and iron are typically produced together in supernova nucleosynthesis. Deviations from expected ratios can therefore reveal details about the parent system's formation environment. Atypical nickel enrichment might indicate unusual supernova exposure. Unique condensation sequences in the protoplanetary disk or chemical fractionation, processes not prominent in our solar system. Tracing such anomalies through a larger dataset could map the astrophysical landscape of heavy element distribution, offering insights into how diverse the galaxy's formative events truly were. Ultimately, interstellar objects provide a rare and direct window into the chemistry, history, and diversity of planetary systems beyond our own. They are not theoretical constructs or distant exoplanet spectra, viewed across light years. They are physical pieces of alien star systems drifting close enough for detailed analysis. Every time one enters our solar neighbourhood, it offers a fleeting but profound opportunity to study material shaped by environments we cannot replicate. As detection capabilities advance, the study of these visitors may become one of the most important observational tools for understanding the galaxy's complexity. In this context, the significance of objects like 3I Atlas extends far beyond their immediate anomalies. Each carries information about regions of the galaxy inaccessible to our telescope's conditions. We cannot observe directly, and history is written long before the Sun existed. Scientific progress will depend on recognizing these objects not as curiosities, but as essential components of a broader empirical archive, a distributed natural library of cosmic evolution preserved in ice and dust drifting silently between the stars. The unusual presence of nickel in the spectrum of 3I Atlas, unaccompanied by iron, represents one of the most scientifically compelling anomalies associated with this interstellar object. In astrophysical environments, nickel and iron are not merely related, they are fundamentally linked. Both elements are forged in the intense nuclear environments of supernovae, particularly during explosive silicon burning, where isotopes of nickel, especially nickel-56, form abundantly before decaying into iron-56. As a result, comets and asteroids originating in our solar system consistently display tightly correlated nickel-to-iron ratios, a consequence of the uniform chemical inheritance from the Sun's parent molecular cloud. When nickel is detected, iron is expected alongside it. For 3I Atlas, this expectation fails. Spectroscopy indicates strong nickel emission lines, emerging at distances and temperatures where metallic sublimation should not occur. This detection alone is remarkable. Metals typically require substantial heating before vaporizing. Yet the more perplexing issue is the near absence of iron in the corresponding spectral bands. The asymmetry challenges established models of cometary composition and sublimation, suggesting that either the parent system underwent unusual nucleosynthetic enrichment, or that chemical processes in its protoplanetary disk created fractionation pathways uncommon in our solar system. Even if iron is present below the detection threshold, the strength of the nickel signal relative to the muted iron response implies a compositional deviation significant enough to merit deeper investigation. One possibility is that 3I Atlas formed in an environment dominated by supernova ejecta with an atypical nickel-to-iron yield. Different types of supernova produce distinct abundance patterns. Type Ia supernovae, for instance, generate relatively large amounts of nickel compared to core collapse supernovae. If the birth cloud of the comet's parent system was enriched by an unusual mix of supernova remnants, perhaps one dominated by Type Ia contributions, its elemental distribution could naturally diverge from the solar standard. Such an origin would imply that 3 Atlas carries the chemical fingerprint of a region, shaped by specific and perhaps rare astrophysical events. A second explanation involves chemical fractionation during formation. In some theoretical models of protoplanetary disks, volatile organometallic compounds, such as nickel bound to carbon monoxide, can form under low temperature or high pressure conditions. These compounds sublimate at lower energies than metallic iron, meaning that early solar heating of the comet could release nickel into the coma, while leaving iron locked within silicate grains. If this mechanism is responsible, then Thuricilla Atlas may not be intrinsically iron poor, rather its nickel has been selectively liberated by unique thermal or chemical processes. This scenario would highlight the diversity of condensation and binding mechanisms across stellar systems. A third possibility involves long-term exposure to interstellar radiation. Over millions or billions of years, ultraviolet photons, cosmic rays and high-energy particles can alter the uppermost layers of an object's surface. These processes may preferentially break down or liberate molecules containing certain elements while leaving others relatively untouched. If 3I Atlas spent an extensive period travelling through high radiation environments such as galactic halo regions or areas near past supernova shocks, its outer layers may have acquired a nickel-rich veneer unrepresentative of its deeper composition. This interpretation would suggest that the anomaly provides insights not only into its formation, but also into its interstellar journey. The most speculative explanation, though lacking evidence, involves the consideration of artificial or technological processes. In industrial metallurgy, refining tends to separate metals, creating byproducts with skewed elemental abundances. Hypothetically, if large-scale technological activity occurred in the comet's region of origin, metallic residues could be incorporated into protoplanetary material. While there is no reason to invoke such an explanation for 3 Atlas specifically, the nickel anomaly is an example of the type of irregularity that would in theory warrant scrutiny for technological signatures. Its value lies not in supporting extraordinary conclusions, but in encouraging systematic frameworks for interpreting unusual data. Regardless of its origin, the anomaly underscores the need to expand the comparative database of interstellar object compositions. A single comet with decoupled nickel and iron emissions is a curiosity. Multiple such detections would constitute a pattern. If different populations of interstellar comets exhibit distinct metal signatures, astronomers could map these signatures to specific stellar environments. This would allow interstellar objects to serve as proxies for studying stellar populations far beyond observational reach. Nickel-rich objects might trace regions dominated by certain types of stellar explosions. Iron-heavy bodies might correspond to systems with different nucleosynthetic histories. Variations in trace metals could reveal the chemical evolution of entire galactic regions. In this sense, 3I Atlas is not merely a comet with an unusual spectrum. It is a data point within a broader landscape of galactic archaeology. Its composition holds clues to processes that occurred billions of years ago in a stellar nursery no longer observable. The lack of iron, whether real or apparent, is a signal that the galaxy's chemical diversity extends into realms that defy simple analogy to the solar system. As more interstellar objects are detected, these signals will accumulate, forming a mosaic of elemental signatures that illuminate the history of stars' disks and explosive events across the Milky Way. The scientific response to this anomaly must therefore blend rigour with openness. It is essential to avoid leaping to conclusions while recognising that deviations from established norms often provide the most valuable insights. In the history of astronomy, anomalies have repeatedly acted as catalysts for theoretical refinement and discovery. The nickel signature of 3I Atlas, whether it reflects a rare formation environment, exotic chemistry, surface processing, or an observational artifact, offers an opportunity to expand the conceptual frameworks used to interpret interstellar matter. Ultimately, the significance of the nickel anomaly lies not in its strangeness alone, but in what it represents: evidence that the chemical narratives of other star systems are more varied, more complex, and perhaps more ancient than previously assumed. 3 Atlas carries within it the imprint of a world we will never see. Studying such anomalies is in effect a form of remote archaeological investigation on a galactic scale. Through these analyses, humanity moves closer to constructing a coherent understanding of how planetary systems differ, how they evolve, and how the broader galaxy records its own history through the silent trajectories of objects cast into interstellar space. The discovery of 3 confirmed interstellar objects in just 7 years, Oumuamua in 2017, Tsu'ai Borisov in 2019, and 3 Atlas shortly after, has forced astronomers to reconsider how many of these visitors pass through our solar system unnoticed. Before 2017, no interstellar objects had been directly observed. Their existence was theoretical, inferred from models suggesting that planetary systems eject enormous quantities of debris during their formation. Once Oumuamua was detected, the implications were immediate. If a single brief glimpse could reveal such an object, then the solar system must be constantly traversed by many more that evade detection. Statistical modelling now suggests that at any given moment, several interstellar bodies, comet-sized or smaller, are likely within the orbit of Jupiter. Most remain invisible because they are too faint, too small, or moving too rapidly for current instruments to track. Their presence can be deduced only indirectly from population estimates, detection rates, and observational biases. The 3 we observed were not necessarily unique. We simply happened to look in the right direction at the right time with sensitive enough telescopes. The difficulty lies in the mechanics of detection. Interstellar objects enter the solar system with high relative velocities, typically tens of kilometers per second. They follow hyperbolic trajectories, spending only a short time in regions where terrestrial telescopes can collect adequate photometric or spectroscopic data. Oumuamua, for example, was already moving away from the Sun when it was discovered, leaving only a narrow observational window before it faded beyond instrumental limits. This short visibility period challenges astronomers to classify such objects quickly, often without the luxury of comprehensive follow-up. Improving detection capability requires not only larger telescopes, but also faster survey cadences, broader sky coverage, and more sensitive instrumentation capable of identifying faint, fast-moving objects. The Vera Rubin Observatory in Chile is poised to transform this field when it becomes fully operational. Its legacy survey of space and time will scan the entire visible sky every few nights, increasing the likelihood of identifying interstellar objects inbound rather than outbound. Predictions suggest that Rubin may detect 1 such object per month, enabling a meaningful statistical sample within a decade. With dozens or even hundreds of confirmed detections, scientists will be able to compare compositions, trajectories, and physical characteristics across a population rather than relying on anecdotal cases. Yet detection alone is only the first step. Understanding these objects in detail requires follow-up observations across multiple wavelengths, optical spectroscopy for volatile composition infrared data for dust and thermal properties, and radio observations for molecular signatures. Some interstellar comets may exhibit emission lines or activity patterns that differ sharply from those in our solar system. Others may be inactive rocky bodies that reflect starlight weakly, and therefore require powerful infrared instruments to detect. The diversity among the first 3 examples indicates that a broad observational strategy will be essential to capture the full range of possibilities. Beyond remote observation lies a more ambitious prospect: physically intercepting an interstellar object. Such a mission would represent a profound leap in space exploration, offering the opportunity to collect direct samples from a body formed around another star. Achieving this, however, presents formidable technical challenges. Interstellar objects typically traverse the inner solar system at high velocity, leaving only a limited time frame for launch and intercept. An intercept mission would need to be designed for rapid deployment, high acceleration, and flexible targeting characteristics not easily achieved with current space propulsion technologies. Nevertheless, conceptual mission designs have been proposed. Some involve storing a spacecraft in heliocentric orbit, ready to redirect toward a newly detected interstellar target. Others suggest using advanced propulsion methods such as solar electric propulsion, or even solar sails to achieve the high velocities needed for rendezvous. A more speculative avenue involves gravitational assists or perihelion maneuvers close to the Sun, enabling extreme acceleration by exploiting solar radiation pressure or gravitational slingshot effects. While these ideas push engineering to its limits, they lie within the realm of physical possibility. The scientific return from such a mission would be extraordinary. A lander or sampler that could drill beneath the irradiated surface layers of an interstellar comet might uncover pristine ices and materials unchanged for billions of years. Laboratory analysis of isotopes, minerals, and organic structures would provide insights unavailable from remote spectroscopy alone. The ratios of heavy elements could reveal the type of supernovae that enrich the parent cloud. Carbon and nitrogen isotopes could point to specific nucleosynthetic environments or evolutionary histories. Organic compounds, if present, might shed light on the prevalence of prebiotic chemistry in the galaxy. Such samples could even test hypotheses concerning the distribution of life's building blocks across interstellar space. While the survival of intact microorganisms during long interstellar journeys remains unlikely, complex molecules could persist if shielded within thick ice. Detecting or ruling out such chemistry would have profound implications for understanding how common the prerequisites for life may be across planetary systems. As our detection capabilities improve, the unseen population of interstellar objects may become one of the most important research frontiers in astrophysics. Each object offers a unique snapshot of the chemical diversity of planetary systems. Together, these objects form a natural sampling of galactic history material, launched from countless stars across different epochs, scattered through space by gravitational interactions, stellar evolution, and chaotic dynamical processes. By studying them, we gain insight not only into other worlds, but into the broader structure of the Milky Way and the forces that shape it. The emerging realization is that interstellar objects are not rare cosmic accidents, but routine wanderers. They carry stories from distant systems, stories inscribed in their elemental composition, mineralogy, and volatile content. Until recently, we lacked the capability to notice them. Now, with modern surveys and technological advances, the galaxy is beginning to reveal these hidden emissaries. As the catalogue grows, so too will our understanding of how planets form, how chemistry varies from one region of the galaxy to another, and how materials are exchanged across vast interstellar distances. These objects remind us that our solar system is not isolated. It is embedded in a dynamic galactic environment where matter circulates widely and unpredictably. By studying the visitors that pass briefly through our celestial neighbourhood, we are effectively reading chapters of a galactic narrative written long before the Sun existed. As future missions aim not only to observe but to intercept and sample these objects, the scientific opportunities will expand further, enabling direct examination of material from worlds that orbit stars we may never reach. In this sense, the unseen population of interstellar objects is not merely a curiosity, it is a key to understanding the galaxy itself. As detection rates rise, each new object will deepen the empirical foundation upon which models of planetary formation, stellar evolution, and galactic chemistry are built. The silent wanderers moving through our solar system carry answers to questions we have only begun to articulate. Their increasing visibility marks the beginning of a new era in astronomy, one where the galaxy's history arrives at our doorstep, one visitor at a time. Astronomy has entered an era defined not by a lack of information, but by an overwhelming surplus of it. Modern observatories generate data at rates inconceivable a century ago, radio arrays that monitor the sky continuously orbiting telescopes that detect fluctuations invisible to the human eye, automated surveys that scan billions of celestial objects each night. This influx has transformed the discipline from one in which anomalies were rare and precious, to one where they appear with striking regularity. These anomalies, odd radio circles, millisecond radio bursts, unexplained light curves, interstellar wanderers challenge astronomers not because they are inherently inexplicable, but because the pace of discovery exceeds the pace of theoretical interpretation. In the 20th century, the observational landscape was far sparser. Researchers might spend months gathering data on a single object, capturing only small slices of the cosmic environment. When something unusual appeared, an unexpected emission line or a strange brightness variation, it commanded immediate attention. The limited volume of available data meant that each discovery had sharp scientific focus. The discovery of pulsars, for example, emerged from detailed study of peculiar repeated radio pulses reluctantly labelled LGM-1 because the regularity resembled artificial signalling. Astronomers devoted intense scrutiny to this singular anomaly until it yielded to natural explanation. Today, the situation is reversed. The universe has not become more chaotic, our instruments have become more perceptive. By observing more of the sky more often with greater sensitivity, we have revealed phenomena that once escaped notice entirely. This has produced an environment where anomalies accumulate faster than the theoretical frameworks needed to interpret them. The result is a scientific landscape in which unexplained events coexist with mature explanations, and distinguishing between them is an ongoing iterative process. This abundance of anomalies creates both opportunity and risk. On one hand, unexplained observations are fertile ground for new physics. Pulsars, gamma ray bursts, dark energy, and gravitational waves all emerge from initially mysterious signals. On the other hand, the modern attention economy amplifies anomalies before the scientific community has time to contextualize them. A single ambiguous signal can circulate globally within hours, spawning speculation that ranges from serious theoretical inquiry to outright fiction. This rapid dissemination shapes public perception and complicates the careful, methodical work required to evaluate competing hypotheses. The case of Tabby's star illustrates this dynamic with precision. Its irregular dimming patterns were intriguing, but not unprecedented. Variable stars and obscuring dust clouds have long been studied. Yet the scale and irregularity of its brightness drops prompted speculation about alien megastructures, a concept that captured public imagination immediately. Once high-impact interpretations enter public discourse, they become difficult to dislodge even when more conventional explanations emerge. Dust, for example, became the leading hypothesis for Tabby's star, supported by wavelength-dependent dimming. Yet this scientifically grounded explanation did little to quell the public appetite for extraordinary alternatives. A similar process unfolded with Oumuamua. While scientists proposed natural causes for its acceleration, such as exotic ices or radiation-driven dynamics, the mere possibility of an artificial origin dominated headlines. This pattern reveals a consistent sociological trend. When data are ambiguous, the highest impact interpretation often becomes the most visible, regardless of likelihood. Human cognition is drawn to explanations that produce emotional resonance, even when those explanations require more assumptions than simpler mundane ones. The proliferation of anomalies is not, however, evidence that the universe is behaving unpredictably. It is evidence that our observational capabilities have outpaced our interpretive frameworks. For every anomaly that points to a new physical process, many more likely arise from observational noise, incomplete data, or edge cases of known phenomena. The challenge is determining which is which. This requires not only advanced instrumentation, but also careful statistical reasoning replication across independent observatories and a willingness to revise models in light of new evidence. In this context, 3I Atlas is not an isolated curiosity, but part of a broader pattern. Its unusual water production rate, nickel emission lines, and chemical behaviour add to a growing catalogue of phenomena that operate at the edges of current understanding. Whether these anomalies ultimately lead to revised models of cometary chemistry or new insights into interstellar material transport, their significance lies in the questions they provoke. The accumulation of such anomalies pushes astronomy toward deeper, more integrated theoretical frameworks capable of explaining a wider range of observations. This scientific environment demands a balanced approach. Curiosity must be tempered by discipline, speculation must yield to evidence, imagination must coexist with methodological rigour. Hypotheses should accommodate the full range of possibilities without privileging extraordinary explanations prematurely. Equally, skepticism should not become dogmatic dismissal. Many transformative discoveries began as anomalies dismissed by contemporaries, as measurement errors or observational oddities. One of the most important lessons from modern astronomy is that anomalies rarely point to singular causes. Instead, they reveal limitations in our current models, biases in our observational coverage, or complexities in natural systems that were previously inaccessible. The stacking of anomalies, comets with unusual chemistry, stars with irregular dimming, unexplained radio structures may or may not signify a unified underlying phenomenon. They may instead reflect the simple reality that the universe is more varied than the subset of it we historically observed. Nevertheless, the growing list of unexplained phenomena highlights the need for improved frameworks that connect disparate domains. Theoretical astrophysics must adapt to a future where anomalies are routine, and where distinguishing between noise, natural oddities, and truly novel physics becomes increasingly challenging. This will require integrating multi-wavelength data, leveraging machine learning for anomaly classification, and maintaining strong interdisciplinary communication between observational astronomers, theorists, and instrument designers. In the end, the significance of these anomalies lies not in their strangeness, but in their capacity to reveal gaps in our knowledge. They serve as signposts marking the boundaries of current understanding, pointing toward the questions that next-generation astronomy must address. As detection technologies improve the rate of anomaly, discovery will continue to accelerate. Each new irregularity will join a growing archive of unexplained signals that collectively reflect the evolving complexity of our observations. The task of contemporary astronomy, therefore, is not to resolve every anomaly immediately, but to cultivate a disciplined curiosity, recognizing that some anomalies will evaporate under scrutiny, while others will redefine entire fields. The dense accumulation of unexplained phenomena is not a failure of science, but a testament to how rapidly our empirical reach has expanded. In this expanding frontier, the anomalies themselves become essential tools. They illuminate the edges of what is known and push the boundaries of what may yet be discovered. The study of 3 Atlas brings us to a familiar scientific crossroads, an object behaving in ways not fully predicted by existing models, and a community forced to reconsider which assumptions remain valid and which require refinement. This interstellar comet, active at unusual distances, shedding water where water should not sublimate, releasing nickel without detectable iron, and expressing a volatile inventory unlike any catalogued in our solar system, exemplifies the tension between natural explanation and interpretative uncertainty. Yet this tension is precisely where scientific progress gains momentum. At the centre of the analysis lies the question of whether strangeness necessarily implies the extraordinary. The scientific answer is almost always no. Nature routinely produces complex counterintuitive behaviour, particularly in environments unfamiliar to human experience. The mere fact that an object appears intentional or alive in its activity pattern does not demand a biological or artificial explanation. Physical systems frequently emulate purpose when they are simply following thermodynamic pathways or responding to environmental gradients. The challenge is not to explain away anomalies, but to understand the underlying mechanisms that generate them. For 3I Atlas, the most plausible interpretation remains fully natural. The unusual water production rate may reflect reservoirs of ice insulated beneath volatile CO2 layers that activate at lower temperatures. The nickel anomaly could result from fractionation processes in the parent disk, or from unique organometallic compounds formed under exotic chemical conditions. The unusual carbon dioxide dominance may correspond to formation close to the parent star, or to a disk with different condensation boundaries. Each hypothesis fits within known physical frameworks, even if those frameworks must be broadened to accommodate environments not previously observed. Yet the scientific value of 3I Atlas does not depend on whether the comet fits neatly into existing categories. Its significance arises precisely because it does not. Every deviation forces reconsideration of assumptions that have remained unchallenged simply because the solar system offered no counterexamples. The fundamental limitation of solar system science is that it is based on a sample size of 1. The same processes that shape comets here may be rare elsewhere, while processes common in other systems may be absent or muted in ours. An interstellar visitor reveals what our observational bias conceals, that the galaxy contains more chemical and structural diversity than any single planetary system can display. In this way, 3I Atlas acts as a corrective to anthropocentric science, reminding researchers that the familiar is not necessarily the universal. The comet's behaviour challenges tightly coupled relationships between volatiles and temperature between metal, and sublimation thresholds between observable activity and proximity to the Sun. Even its trajectory, hyperbolic and unbound, reflects a history that predates the Sun itself by potentially billions of years. It is not merely an object passing through the solar system. It is a fragment of an older galactic chapter, carrying within it the chemical memory of long-extinct stars. The temptation to speculate about artificial origins arises in part because anomalies evoke narratives. When data defy expectations, the human mind seeks intentionality. However, extraordinary explanations require extraordinary evidence, a standard not met by any observations of 3I Atlas to date. No trajectory irregularities suggest propulsion, no spectral signatures imply engineered materials, and no energy emissions indicate technological processes. The anomaly lies in chemistry and activation thresholds, not in behaviour inconsistent with natural physics. Nonetheless, scientific discipline does not require dismissing unconventional hypotheses outright. It requires ranking them according to plausibility and evidence. While natural explanations dominate the probability space, remaining open to alternative possibilities ensures that discovery is not hindered by confirmation bias. The important distinction is that openness is not equivalent to credulity. A hypothesis gains traction only when it explains the data more effectively than established models. Artificial origin theories do not in this case offer explanatory benefits that exceed those of natural chemistry. The broader lesson from the 3I Atlas case is that anomalies function as catalysts for scientific maturation. They expand the conceptual frameworks used to interpret the cosmos. They motivate new models of comet formation, new laboratory experiments on exotic ices, new simulations of protoplanetary disk chemistry, and new detection strategies for future interstellar objects. They emphasize the need to sample beyond the solar system to avoid mistaking local regularities for galactic norms. 3I Atlas also underscores a deeper philosophical point, that the universe retains an irreducible complexity, one that resists premature closure. Understanding advances through questions, not answers. By challenging our expectations, anomalous objects preserve the vitality of scientific inquiry. They prevent complacency, compel re-examination, and create intellectual space where new theories can emerge. In the final analysis, whether 3I Atlas ultimately proves to be a chemical outlier, a product of unusual stellar enrichment, or a representative of a class of interstellar comets, yet to be sampled, its value lies in what it reveals about the galaxy's diversity. It is a messenger from a system formed under conditions unknown to us, shaped by stars we cannot observe directly, and altered by interstellar processes operating across immense timescales. Studying such an object offers not only empirical insight, but also perspective, reminding us that our solar system is one thread in a tapestry woven from countless stellar histories. As detection capabilities improve and more interstellar visitors appear, the scientific community will gain access to a distributed archive of galactic evolution fragments, of ancient disks, relics, of long-dead stars, carriers, of volatile inventories that reflect the thermodynamics of alien worlds. Each will pose new questions, reveal new anomalies, and extend humanity's understanding of cosmic complexity. In this sense, the greatest significance of 3I Atlas lies not in its strangeness, but in its role as part of a growing empirical bridge between the solar system and the broader galaxy. The comet's anomalies are not disruptions of scientific order. They are signals that our understanding is incomplete, and therefore capable of growth. Through such anomalies, astronomy becomes not a catalogue of certainties, but a dynamic discipline shaped by continual surprise, guided by evidence and grounded in the recognition that the universe remains richer, older, and more varied than any model can yet encompass. The study of objects like 3I Atlas illustrates a profound and often overlooked truth about scientific inquiry. The pursuit of understanding is shaped as much by questions as by answers. An interstellar comet passing briefly through our solar system becomes more than a physical object. It becomes an invitation to consider the limits of current knowledge, the biases inherent in local observations, and the immensity of the galactic environment in which our system is embedded. The universe offers us fragments' ice-dust radiation trajectory, and from these fragments, we attempt to reconstruct history's billions of years long and light years wide. This act is inherently incomplete, but its incompleteness does not diminish its value. When astronomers analyse the behaviour of 3I Atlas, they are not simply describing a comet. They are testing the boundaries of astrophysical models developed largely from solar system analogues. The comet challenges assumptions about volatile activation metallic ratios and the thermodynamic behaviour of frozen compounds in low radiation environments. These challenges do not imply failure, they indicate growth. Scientific frameworks are not static and anomalies are not disruptions, they are catalysts. A model that cannot accommodate a single anomalous data point is a model awaiting refinement. As anomalies accumulate, they push the discipline toward greater nuance. The detection of Oumuamua forced scientists to reconsider how fragile low-density structures behave under solar radiation. The study of 2I Borisov expanded the parameter space of comet-forming environments. The arrival of 3I Atlas adds new dimensions, volatile sequencing, metallic decoupling, and unexpected thermal activation. Each discovery builds upon the last, creating a progressively richer picture of galactic chemistry. The fact that each new object looks different is not a failure of prediction, but evidence that our theories were built from too small a sample size. The realization that our solar system represents only one instance among countless planetary systems is not new, but interstellar objects make this realization tangible. They provide physical specimens of alien environments, fragments of systems shaped by different stars, different radiation fields, and different histories of elemental enrichment. Where telescopes can observe only the aggregate light of distant stars and disks, interstellar objects offer direct access to solid matter, shaped by processes largely inaccessible to remote observation. In this way, each visitor represents an opportunity to expand the empirical foundations of planetary science. The growing catalogue of unexplained or partially explained astronomical events reflects the increasing complexity of the observational landscape. Fast radio bursts, odd radio circles, anomalous dimming events, unexpected chemical signatures all contribute to the impression of a universe that behaves unpredictably. Yet unpredictability often reflects the limits of current measurement, not an absence of underlying order. The true challenge lies not in the anomalies themselves, but in the pace at which they accumulate. Modern instruments detect more phenomena than the current generation of theories can absorb, forcing astrophysics to operate in a space of provisional understanding. This provisionality is not a weakness, it is a mark of scientific maturity. In such an environment, it becomes crucial to maintain a careful balance between openness and skepticism. Extraordinary explanations may capture imagination, but ordinary processes often prove sufficient once the full scope of data is available. At the same time, rigid adherence to familiar explanations can obscure genuine opportunities for discovery. The history of astronomy is filled with examples where unexpected behaviour, pulsars, quasars, dark matter eventually revealed new physical principles. The value of anomalies lies in their ability to disrupt complacency. They expose assumptions taken for granted and reveal the hidden complexity behind seemingly stable phenomena. They compel researchers to design better instruments, refine analytical methods, and generate predictive models capable of accommodating diversity. The process of confronting these anomalies strengthens the discipline even when the anomalies ultimately prove consistent with natural processes. With interstellar objects, this dynamic is particularly pronounced. Their trajectories carry them across stellar boundaries, through radiation fields, and across regions of the galaxy, with distinct chemical histories. Each object is a record of multiple environments, its formations, its ejection, and its interstellar journey. The opportunity to study such an object is fleeting once it leaves the solar system. The data-gathering window closes permanently. This urgency underscores the need for rapid detection systems, flexible observational strategies, and future intercept missions capable of direct sampling. Such missions may eventually transform interstellar object research from remote spectroscopy to hands-on analysis. A single retrieved sample could provide isotopic ratios, organic inventories, and mineral structures impossible to derive from telescopic data. These measurements could offer unprecedented insight into the chemistry of distant regions of the galaxy, enabling researchers to reconstruct not only the history of a single object, but the evolutionary pathways of the environments from which it originated. The broader implication is that the Milky Way is not static. It is a dynamic ecosystem in which matter circulates across stellar populations, carrying signatures of formation and destruction, events across vast distances. Interstellar objects serve as traces of these processes, revealing the interplay between supernovae molecular clouds and planetary formation. By studying them, scientists can decode the history of the galaxy, written in the chemistry of wandering debris. The ultimate lesson from 3I Atlas and from anomalies in general is that the universe remains deeper, older, and more intricate than any human framework can fully contain. Scientific understanding advances by acknowledging uncertainty, embracing complexity, and allowing evidence to reshape assumptions. Anomalies are not obstacles, but pathways, reminders that discovery is an ongoing process rather than a finished product. As more interstellar visitors pass through the solar system, astronomy will increasingly operate at the intersection of observation, interpretation, and humility. Each new object will challenge existing models. Some challenges will dissolve under scrutiny, while others will prompt significant revisions. Through this iterative process, the field will graduate toward a more comprehensive understanding of planetary diversity, stellar evolution, and galactic structure. 3I Atlas is one such challenge, neither a contradiction of known physics nor a validation of extraordinary speculation, but an opportunity to refine the scientific portrait of the galaxy. Its significance lies not in its anomalies alone, but in the way those anomalies illuminate the vastness of what remains to be understood. Through objects like this, the cosmos reveals itself not as a solved puzzle, but as a living archive endlessly inviting deeper study. In this sense, the comet is not merely a visitor, but a reminder our models are temporary, our knowledge partial, and our curiosity essential. At the conclusion of any scientific investigation into an anomalous object like 3I Atlas 1 inevitably arrives at a point where empirical analysis intersects with philosophical reflection. The comet, with its unexpected water production, unusual metal emissions, and unfamiliar chemical profile, provokes questions that reach beyond spectroscopy and orbital mechanics. It forces us to consider what it means to encounter something that behaves differently from our expectations, and how such encounters shape our understanding of both the universe and ourselves. In many ways, 3I Atlas becomes not merely an object of study, but a symbol of how science advances through confrontation with the unfamiliar and sustained curiosity about what lies beyond current knowledge. The natural explanation for the comet's behaviour remains the most consistent with available data. Its activity patterns, though unusual for objects in our solar system, can be understood through expanded models of volatile chemistry, layered sublimation behaviour, and formation environments characterised by different elemental abundances. The presence of abundant carbon dioxide, the delayed release of cyanide, and the anomalous nickel emissions likely reflect conditions specific to its parent star system. These features challenge the assumption that cometary behaviour observed in the solar system is universally representative. Instead, they underscore a broader truth: planetary systems across the galaxy form under diverse conditions, producing bodies with correspondingly diverse compositions. The scientific implications of this diversity are profound. Until recently, models of cometary activity were constrained by the narrow range of objects available for study. Solar system comets, while varying in detail, share overarching similarities because they emerge from the same protoplanetary environment. Interstellar visitors break this uniformity. They expand the parameter space of what comets can be, how they form, how they evolve, and how their internal chemistry responds to stellar radiation. With each new detection, the catalogue of possible behaviours grows, revealing that the solar system occupies only a small corner within a vast spectrum of galactic chemical realities. Yet beyond the scientific significance, interstellar anomalies expose something about human cognition. We are naturally drawn to the unexplained. When an object deviates from familiar patterns, the mind searches for meaning. This impulse is not irrational, it is a fundamental aspect of pattern, recognition, and evolutionary adaptation shaped by the need to respond to uncertainty. In the absence of full information, high-impact explanations often gain disproportionate attention. This dynamic is visible in public speculation around 3I Atlas, as it was in the cases of Oumuamua and Tapis star. The same psychological mechanisms that once helped humans distinguish threats from noise now influence how we interpret cosmic anomalies. This does not diminish the scientific process. Instead, it highlights the importance of maintaining a disciplined distinction between imaginative possibilities and evidence-based conclusions. Theoretical consideration of artificial origins, for example, is not inherently unreasonable. In any scientific investigation, all hypotheses must be examined before any are accepted or discarded. But evidence is the arbiter, and in the case of 3I Atlas, no observations require invoking artificial or biological explanations. Natural processes, even if unusual, remain sufficient to account for all known data. A commitment to methodological rigour ensures that scientific inquiry remains grounded while allowing exploration of unconventional ideas when warranted. The broader context of anomalies in astronomy reinforces this perspective. The accumulation of unexplained signals across different domains, radio structures, brightness irregularities, interstellar chemistry, does not necessarily indicate a unified phenomenon. Instead, it reflects the expansion of observational capabilities. As our tools grow more sensitive, we detect phenomena previously invisible. Some anomalies dissolve upon deeper study. Others become the seeds of new scientific fields. The key is to allow evidence to shape interpretation, rather than allowing interpretation to dictate what counts as evidence. 3I Atlas is thus best understood not as a singular enigma, but as part of a growing empirical archive documenting the diversity of the galaxy. It represents a data point in a vast emerging data set of interstellar chemistry. Its anomalies may eventually align with findings from future interstellar comets, forming patterns that guide new models of planetary formation. Or they may remain outliers reflecting rare processes or environments. Either outcome contributes to scientific progress by expanding the space of possibilities that models must consider. In a broader sense, the comet invites reflection on the nature of scientific discovery itself. Science advances not through the accumulation of certainties, but through the careful investigation of uncertainties. Anomalies are the mechanisms by which the universe signals the need for deeper examination. They reveal the mismatch between theoretical assumptions and empirical reality, prompting revision and refinement. This process is iterative and ongoing, shaped as much by failures and dead ends as by successful predictions. The willingness to question, revise and adapt is the hallmark of a robust scientific methodology. What makes 3I Atlas particularly compelling is its status as an interstellar messenger. Unlike the distant light from stars or the aggregated signatures of exoplanet atmospheres, this comet represents material that physically originated beyond the solar system. It is a fragment of a planetary environment we cannot observe, directly passing close enough for detailed study only for a brief period before disappearing forever. In this way, the comet acts as a time capsule preserving chemical information from an earlier era of the galaxy's evolution. Studying it is a rare opportunity to sample the conditions of a distant stellar nursery, one shaped by processes that no longer operate in the same way today. As more interstellar objects are detected, astronomy will gradually shift from a solar system-centric discipline to a galactic one. Instead of relying solely on the Sun's planetary environment to define what is typical or possible, researchers will assemble a distributed database of materials from dozens or hundreds of systems. This broader sampling will refine theories of planetary formation, illuminate the diversity of chemical environments, and offer insights into the prevalence of key ingredients necessary for prebiotic chemistry. Ultimately, 3I Atlas is a reminder of the provisional nature of scientific knowledge. Our models are tools, not conclusions. They evolve as evidence accumulates. The comet's anomalies challenge us to refine existing theories without abandoning the cautious skepticism that underpins scientific integrity. They illustrate that understanding the universe requires not only rigorous analysis, but also humility, a recognition that the cosmos is older, larger, and more varied than any human framework can fully describe. As the 3I Atlas continues its trajectory and eventually leaves the domain of observation, it will remain part of an ongoing conversation between humanity and the universe. Each anomaly it presents becomes a question, each measurement a clue, each contradiction an invitation to think differently. In this sense, the comet is not merely a physical object, but a participant in the scientific dialogue, a reminder that the universe is not static but dynamic, not fully known but continuously revealing itself. The significance of 3I Atlas lies not in whether it aligns with our expectations, but in how it challenges them. By prompting new questions and highlighting the limits of current understanding, it advances the scientific process. Through such objects, we come to see the galaxy not as a distant abstraction, but as a complex and evolving system whose history is written not only in light, but in the silent trajectories of wanderers from other stars. And in studying them, we learn not only about the cosmos, but about the nature of inquiry itself, restless, uncertain, and endlessly driven by the desire to understand. The investigation of 3I Atlas, along with the growing catalogue of astronomical anomalies that define modern astrophysics, ultimately leads to a larger and more consequential realization. The universe does not present itself to us in neat categorized fragments. It reveals itself in scattered signals, partial data, and fleeting encounters. The task of science is to impose structure on this complexity without oversimplifying it, to seek coherence without assuming completeness, and to recognize that discovery often begins where certainty ends. In the last several decades, astronomy has shifted from a discipline constrained by limited observation to one inundated by data. This transformation has exposed a surprising truth. Anomalies are not exceptions, but an expected outcome of expanding observation. When we observe more of the sky across more wavelengths with greater sensitivity, we inevitably find more phenomena that fail to fit established models. Odd radio circles, fast radio bursts, transient events, with no clear origin, stars that dim unpredictably, interstellar objects with unprecedented chemistry. Each anomaly adds a new thread to a tapestry far more intricate than the models built from 20th century observations could anticipate. For many, the proliferation of anomalies suggests a universe growing stranger. But in reality, the universe is not changing, we are. Our tools have improved faster than our frameworks. This mismatch creates a temporary sense of dissonance, as though the cosmos has become unstable. In truth, the cosmos has always been this complex. We simply lack the capacity to perceive it in sufficient detail. The challenge now is to interpret this complexity responsibly, without yielding to premature conclusions or unfounded speculation. The temptation to unify disparate anomalies into a single explanation, or to attribute them to extraordinary causes, arises naturally from human cognition. Pattern recognition, the brain's fundamental mechanism, constantly seeks coherence even when evidence is incomplete. When multiple unexplained events emerge close together in time, it is easy to imagine connections. Yet statistical reasoning and scientific discipline remind us that coincidence does not imply causation. Anomalies may cluster simply because our observational systems have finally reached a threshold where subtle phenomena become visible. 3I Atlas exemplifies this dynamic. Its unusual chemistry, early activation, and metal anomalies are striking, but they do not represent violations of physical law. Instead, they reveal limitations in our understanding of planetary formation across diverse stellar environments. Rather than indicating a universal anomaly, the comet illustrates the variety that naturally arises when countless star systems evolve independently over billions of years. That its behavior feels unfamiliar reflects our limited exposure, not the rarity of such objects in the galaxy. This broader recognition calls for a more mature model of scientific interpretation, one rooted in humility as much as in curiosity. Humility acknowledges that our theories are provisional, shaped by incomplete sampling and subject to revision. Curiosity ensures that anomalies are pursued with rigor, not dismissed simply because they do not conform to prior expectations. Together, these principles form the foundation of scientific resilience, the ability to adapt, refine, and expand knowledge in response to new evidence. At the same time, the cultural dimension of anomaly interpretation cannot be ignored. Public engagement with astronomy has never been higher, driven by accessible data, online discussion, and a collective fascination with the unknown. But heightened engagement brings the risk of distortion. Speculation spreads faster than correction, and ambiguity invites narratives that overshadow empirical analysis. The responsibility of the scientific community therefore extends beyond research. It includes communicating uncertainty, clearly resisting sensationalism, and providing context that empowers the public to distinguish between informed hypotheses and speculative extrapolation. Yet this interplay between science and culture also underscores the enduring power of cosmic phenomena to stimulate imagination. Anomalies ignite the same sense of wonder that has driven exploration since antiquity. While the scientific method demands restraint, the emotional resonance of these anomalies reminds us that discovery is not a purely intellectual pursuit. It is also existential. When confronted with objects like Three-Eye Atlas, we glimpse the vastness of the galaxy and our own small position within it. Such encounters deepen our sense of connection to a universe that is profoundly indifferent to our presence, yet endlessly generous in offering mysteries for us to solve. In this light, the proliferation of anomalies becomes less a source of confusion and more a sign of progress. They signal that we are finally observing the cosmos at a level commensurate with its complexity. They mark the shift from a local to a galactic perspective, in which our theories must evolve to incorporate the chemical, structural and dynamical diversity of planetary systems formed under conditions far different from those of the Sun. The future of astronomy will increasingly depend on integrating these anomalies into coherent frameworks. Missions designed to intercept and sample interstellar objects may transform our understanding of galactic chemistry. Advances in machine learning may help classify transient events and distinguish true anomalies from noise. Multi-wavelength observatories will continue to reveal layers of complexity previously hidden from view. Collectively, these developments will move the discipline toward a deeper, more unified understanding of the galaxy. In the end, Three-Eye Atlas serves as a microcosm of this broader shift. It is one object among billions, yet its brief passage through the solar system provides a wealth of evidence about environments we cannot observe directly. It reminds us that scientific progress is built not on stable conclusions, but on the constant negotiation between expectation and observation. The comet's anomalies are not puzzles to be solved in isolation, but components of a larger narrative in which the universe continually invites us to revise our understanding. What emerges from this process is a more accurate and more expansive view of the cosmos, one that recognizes diversity as the rule, rather than the exception, one that sees anomalies not as threats to theory, but as engines of progress, and one that affirms the essential truth at the heart of scientific inquiry that understanding grows through questioning, and questioning grows through the willingness to confront the unknown. As the catalogue of interstellar objects grows and astronomical anomalies accumulate, a deeper question emerges, one that transcends chemistry, spectroscopy, or orbital dynamics. It concerns the long arc of humanity's engagement with the cosmos, and how these brief encounters with matter from other stars influence humanity's long-term intellectual trajectory. The scientific study of objects like Three-Eye Atlas is on the surface an exercise in empirical analysis, measurements of volatile emissions, modelling of trajectory perturbations, refinement of cometry activation models. Yet beneath these technical pursuits lies a more fundamental process, the gradual expansion of our conceptual horizon. For most of human history, cosmic inquiry was limited to objects within the solar system, or to the light of distant stars. Every element of scientific understanding was shaped by proximity. Planets, moons, and comets belong to a single gravitational system, all sharing the same parent star, the same broad chemical inheritance, and the same evolutionarily stable environment. The uniformity of these bodies created a natural bias. Astronomers assumed that what held true for the solar system would hold true everywhere else. That assumption was not unreasonable, it was simply a consequence of limited sampling. Interstellar objects disrupt this assumption with a clarity no telescope alone can provide. Unlike distant exoplanets whose atmospheres are inferred from faint spectroscopic signals, interstellar comets are tangible physical visitors. They offer direct access to the solid-state chemistry of alien systems, bypassing the interpretative constraints of remote sensing. Their presence within the solar system creates a new category of evidence, one not filtered through stellar glare or atmospheric interference. And because they originate from environments shaped by processes foreign to the Sun's formation history, they reveal how narrow our prior sampling has been. This shift has implications that extend beyond astronomy. It forces a re-evaluation of how scientific models are constructed and how confidently conclusions can be generalized. The assumptions underpinning many theories from pre-Bartic chemistry to planet formation paradigms were built on the implicit expectation that solar system patterns represent universal norms. As interstellar samples accumulate, this expectation becomes increasingly difficult to maintain. Diversity rather than uniformity appears to be the galactic standard. Yet this realization does not diminish the value of existing theories. Rather, it contextualizes them. They describe one instance of a broader cosmic distribution, one branch in this evolutionary landscape populated by planetary systems formed under radically different conditions. This broader view invites new questions. Which chemical pathways recur across multiple systems? Which processes are rare but significant? How do variations in stellar metallicity radiation, fields and disk turbulence influence the formation of comets, asteroids and planets? These questions illustrate a deeper trend. Astronomy is transitioning from a discipline focused on the solar system to one that situates the solar system within a galactic framework. Interstellar objects are not curiosities, but essential data points in a distributed archive of planetary system diversity. Their trajectories are chance intersections between our observational reach and the galaxy's dynamic exchange of matter. Each detection is a reminder that planetary systems do not evolve in isolation. They eject material into interstellar space, and that material becomes part of the chemical ecosystem through which stars and planets form. The future of this field will depend on technological, theoretical and philosophical advances. On the technological front, rapid response observation systems will be essential. The fleeting nature of interstellar visitors necessitates immediate detection and characterization. Robotic intercept missions, long viewed as speculative, may become central to planetary science. If spacecraft can rendezvous with and sample these objects, the boundary between observational astronomy and laboratory chemistry will blur, providing unprecedented access to material from environments that predate the Sun. The theoretical dimension will require new models capable of integrating heterogeneous data. The diversity of interstellar compositions will challenge existing paradigms, prompting a shift from models based on singular evolutionary tracks to frameworks that incorporate probabilistic distributions across multiple formation environments. This will affect disciplines ranging from astrophysics to astrobiology, reshaping assumptions about the prevalence of organic precursors, the stability of habitable environments, and the likelihood of life emerging under varying conditions. Yet the philosophical implications may be the most enduring. Interstellar objects, though rare in direct encounter, symbolize a universe far more interconnected than previously imagined. Material from distant systems traverses the galaxy, crossing light years of empty space before passing briefly through another star's domain. These trajectories are silent reminders of cosmic continuity, a continuity indifferent to human presence yet profoundly relevant to humanity's understanding of its place in the cosmos. The arrival of objects like 3i Atlas represents more than a scientific opportunity. It represents a shift in perspective. It invites us to consider that our solar system is not a unique or privileged environment, but one among countless others, each contributing its own fragments to the galactic medium. These fragments in turn shape the systems that follow, creating an ongoing exchange of matter that transcends stellar boundaries. In this sense, interstellar objects are the physical manifestation of a galaxy that is not static, but dynamic, not isolated, but interconnected. As more of these visitors are detected, humanity will face a new kind of discovery, not the discovery of alien life or exotic physics, but the discovery of galactic context. The understanding that our solar system is an emergent product of processes operating across millions of years and trillions of kilometers. The understanding that diversity, not uniformity, is the fabric of planetary formation. And the understanding that knowledge itself is provisional, continually reshaped by new evidence and new encounters. In the long arc of scientific progress through Atlas and objects like it, serve as milestones marking humanity's transition into a genuinely galactic species, not in the sense of physical expansion, but in the sense of intellectual reach. As humanity continues to study these visitors, the models of planetary science, stellar evolution, and chemical distribution will expand, and with them the boundaries of human understanding will expand as well. In this sense, the significance of these interstellar wanderers lies not only in what they are, but in what they represent the beginning of a deeper, broader, and more accurate comprehension of the galaxy and humanity's place within its ancient, ongoing, and ever-unfolding story. The emerging study of interstellar objects marks a turning point in astronomy, not because each new object provides dramatic revelations, but because collectively they redefine what it means to study the universe scientifically. They highlight a shift from a perspective bounded by the solar system to one shaped by the full scale of the Milky Way. This transition is not sudden. It is incremental, marked by a slow accumulation of evidence, anomalies, and unanswered questions. Yet its implications are profound, influencing how scientific models are constructed, how theories are compared, and how humanity situates itself intellectually within a cosmos far more diverse than once imagined. At the foundation of this transformation lies a recognition that scientific understanding is inseparable from the scope of available data. For centuries, the solar system served as the primary laboratory for testing theories of planetary formation, volatile chemistry, and small body dynamics. This provided stability observations were plentiful, and their common origin ensured that broad patterns emerged. But this stability came with hidden assumptions. It encouraged the belief that the processes seen in the solar system were representative of galactic norms. Now, with increasing access to interstellar material, these assumptions must be re-evaluated. Interstellar visitors highlight the inadequacy of treating the solar system as a template for all planetary systems. Their divergent chemistries and activation patterns reveal that planets and comets form under conditions more variable than our models have historically assumed. Even concepts believed to be universal, such as the relationship between distance from the star and the distribution of volatiles, appear far more flexible when examined across the larger galactic environment. This recognition forces a more probabilistic, less deterministic approach to modelling. Instead of seeking a single correct theory, astronomers must embrace frameworks capable of accommodating a wide range of initial conditions. As scientific models expand to incorporate such diversity, a parallel shift occurs in the cultural dimension of astronomy. Public perception of science often hinges on the expectation of definitive answers, yet anomalies, including those presented by Thry Atlas, demonstrate that uncertainty is not a defect in scientific reasoning, but an inherent feature of genuine exploration. The presence of unanswered questions does not weaken science. It indicates that researchers have pushed far enough into new territory that existing theories must be revised. Communicating this nuance is essential for maintaining public trust and engagement, particularly as discoveries increasingly originate from domains where uncertainty is unavoidable. This new era of cosmic inquiry also raises questions about the future trajectory of scientific research. Studying interstellar objects requires technological innovation at multiple levels, faster detection systems, more sensitive spectroscopic instruments, and perhaps most importantly, spacecraft capable of rapidly intercepting and analysing objects moving at high velocities relative to the solar system. Developing such technologies is not merely an engineering challenge. It marks a shift in how humanity interacts with the broader galaxy. It suggests a future in which the boundaries between Earth-based observation, solar system exploration, and interstellar sampling become increasingly permeable. The intercept missions envisioned by researchers represent a significant conceptual leap. For the first time, humanity would not merely observe interstellar objects, but physically interact with them, touching, sampling, analysing. Such missions would blur the distinction between astronomy and planetary science, introducing new methods of inquiry that combine remote sensing with direct experimentation. The knowledge gained from a single sample return mission could reshape models of cometary chemistry, constrain theories of planetary system diversity, and refine our understanding of the building blocks available at the dawn of stellar formation. Beyond the scientific and technological dimensions, interstellar objects introduce philosophical considerations that reach beyond empirical measurement. They reveal the interconnectedness of the galaxy comets, ejected from distant systems, traverse interstellar space for millions of years before intersecting with our own. These trajectories, seemingly random from a human perspective, illustrate the fluidity of matter across the Milky Way. Material from long-extinct stars shaped by environments fundamentally different from the Sun's can enter our observational domain without warning. This interconnectedness challenges traditional narratives of cosmic isolation. It suggests that the galaxy operates as a dynamic ecosystem in which matter is constantly redistributed. Planetary systems are not closed systems. They exchange material indirectly through the ejection and migration of small bodies. The solar system participates in this exchange as both sender and receiver, a contributor to and beneficiary of the galaxy's chemical evolution. In this context, interstellar objects serve as reminders that boundaries drawn by gravity or light years are not absolute. They are permeable, transient, and subject to the broader flow of galactic dynamics. Such reflections inevitably lead to questions about humanity's intellectual identity. What does it mean to engage with the universe whose complexity exceeds our current conceptual frameworks? What does it mean to build theories that must be revised repeatedly in response to unexpected evidence? The scientific process, often imagined as a march towards certainty, is revealed instead as an ongoing negotiation between models and reality. Interstellar objects make this negotiation explicit. They embody the tension between prediction and observation, between expectation and discovery. As the number of interstellar detections increases, science will move toward a more integrative understanding of cosmic diversity. This does not imply that all mysteries will be resolved. On the contrary, each discovery will likely open new questions. But over time, patterns will emerge, not rigid rules, but statistical regularities that reveal how planetary systems behave across the broad spectrum of galactic environments. Humanity's understanding will shift from a local to a relational perspective, one that situates the solar system within a larger network of stellar processes. Ultimately, the study of interstellar objects marks the beginning of a new phase in scientific history. It signals the transition from a cosmic understanding defined by isolation to one defined by connection. It highlights the fact that the galaxy is not a distant abstraction, but a landscape in which the solar system is merely one participant among billions. And it reinforces the idea that scientific progress depends not on the accumulation of final answers, but on the continual refinement of questions. In this sense, 3R, Atlas, and objects like it are more than anomalies. They are catalysts for intellectual expansion, prompting humanity to confront its assumptions about the universe and its place within it. They remind us that knowledge is never complete, that understanding is always provisional, and that the cosmos, ancient, dynamic, and profoundly diverse, will continue to challenge and inspire us as long as we're willing to look outward and ask. In the end, Traveller, our journey with 3i Atlas brings us to a quiet realization. After all the strange chemistry, the impossible water, the green glow of nickel, what lingers most is not the comet itself, but the act of watching it. A fragment of another star system moved through our sky, and for a moment we followed its path together, two small observers listening for meaning in the dark. The universe did not answer directly, yet its silence felt intentional, like a thought waiting to unfold. Perhaps that is the lesson some mysteries do not close, they simply drift outward, inviting us to wonder without needing resolution. And so we rest in that uncertainty, aware of how vast the cosmos is and how rare it is to pause long enough to feel our place within it. If the night is quiet around you, now let it stay that way. Stay curious, listener. Rest well. The universe will keep watch.